Now again, motivated by this picture, we say that the gradient of f, which we indicate, it's a vector, okay, because clearly fxi plus fyj is a vector. It's a vector, so we're going to have to put an arrow over it. We use this thing called the del operator. It's a delta turned upside down with an arrow over it. Okay, so it's what we call a vector operator that operates on f. And the vector operator, we call the gradient operator. And it's this. And of course, I'll put a circle around this. Okay, so this gradient operator is our representation of the del operator. It's the partial with respect to x of I plus the partial with respect to y of j. Now that's just an operator, just like a derivative operator, okay, a d dx. That's just an operator. You have to apply it to something before it takes a value. So we take this operator and we apply it to f in the obvious way, so that when we apply this to f, we get the partial with respect to x of f times I, partial of f with respect to x times I, and the partial with respect to y of f times j, partial of f with respect to y times j, or as we could denote it, fxi plus fyj. Okay. This gives us the gradient vector, and I should probably note this is a gradient vector. Or just the gradient. It's a vector in the direction of the maximal rate of change of x. And also, I think I've written it down here somewhere, I'm not going to look for it, I'll just tell you, and then we'll find it. Its magnitude is the maximum rate of change of f with respect to distance in any direction. Now, have I actually specified that? Don't think I've written it down, so I'm going to write it down now. Okay, so now we'll make more sense of this later. It's a maximum rate of change. Magnitude is the maximum rate of change of the value of f, the z value you get, with respect to the distance you move in the xy plane. And it happens in this direction. Okay. Just looking at this figure because I hadn't really looked at it. And I want to explain it, but I'm probably going to stop the video and look at it. It's been a couple days since we did this. I want to be sure I see exactly what we're getting at here. But the key here is going to be, okay, now, if u is a unit vector in the direction of motion, then the gradient of f dot u is the rate of change of f with respect to distance for movement in that direction. We can see that in this example. The distance we move here is 1. Okay, so the change that we get in f is just this, and this is the change that occurs when we move through distance 1. Now, if we wanted to actually apply this, we'd most likely be applying it very locally in a small neighborhood of this point. Okay, so the gradient and the directional derivative are more valid for smaller neighborhoods of the point of xy. So I've kind of drawn a smaller neighborhood with a point xy down here in the plane. Should have drawn it more like an ellipse to indicate that it's in the plane, but we get that idea, and we'll work this out. This is the change we would get if the rate of change remained constant and we moved a distance 1 in this direction. If we moved a distance of 0.001 in this direction, we would expect then, because this is a linear approximation, to get 0.001 of the change. So if we multiply this, which is our rate of change in this direction, by the distance that we move in this direction, we're going to get the change in the value of the function. Now, this is just an introduction to the idea of the directional derivative. I'll come back in a minute when I figure out what I was talking about there and talk about it briefly.